Hello everyone, my name is Muzam Hussain from Shanghai Jiaotong University. I'm going to present our paper, a domain-specific benchmark dataset for occluded object affordances estimation in human-object robot interaction. Over the next 5 to 10 minutes, I'm going to walk you through with this outline. First, I'll give you the brief introduction about background, motivation, proposed dataset, experimentations and baselines, results, conclusion, and finally, I'll discuss the future work. The psychologist Gibson coined the term affordance to define the possible interactions between an actor and its environment. In computer vision, the affordance concept has been used in different directions, targeting different tasks. Du et al. And Mears et al. Used deep convolutional neural networks to estimate the part affordances of kitchen and other daily use objects. Swathing et al. Used human forces to estimate affordances of 3D scenes. Emma et al. Jointly modeled human activities and object affordances. Von Funk and his colleague considered the problem of reasoning object affordances through features embedding of demonstration videos. Cheng Yao addressed the problem of affordance reasoning in diverse scenes that appears in real world, more specifically data-targeted social scenes. In journal, our work is on robotic vision. More specifically, we target human-object robot interaction scenarios. The motivation for our work is that we believe in the future human-robot interaction would be more common. Current approaches for object affordance estimation are only dealing with where objects are non-occluded, isolated, static, and no interaction is involved. These approaches are suitable for applications like pick and place. These systems miserably fail when objects are occluded and interaction is involved. The main reason behind these failures is that these systems have been trained on ideal data. We target to estimate object affordances in human-object robot interaction scenarios, which involves challenges like safety, occlusion, and interaction. In order to overcome the flaws of existing approaches and deal with challenges of human-object robot interaction, we propose a novel object affordance dataset, more specifically for human-object robot interactions. For data collection, we adopted egocentric view to make sure the video frames are considered as the view of agent camera. Instead of building a dataset from scratch that is laborious and time-consuming task, we decided to use data from existing dataset and annotate it according to our requirements. We chose FPHA dataset, which is publicly available egocentric RGBD dataset for 3D hand-object interaction from Gracia and et al. We took subset of FPHA dataset which consists of 61 videos, 14 object categories, and 10 activity categories. We named this subset as FPHA-Afford. Then active object in each frame is manually annotated at pixel level. In results, we got 9 affordance classes and 1 background classes. We used VGG annotator as our annotation tool. And then each frame is pre-processed to adjust the field of view using dynamic cropping that dilates the global bounding box by 1000 by 1000 and takes care of image boundaries, dynamically adjusts dilated bounding box. Below are the example of the dynamic cropping. The whole dataset is split into training and testing subsets with nearly 1:1 ratio. The dataset is split at video level rather than frame level. Specifically, there are 2300 frames in training set and 2000 in testing set. In result, we collected 6550 pixel level affordance mask, 4300 frames of 61 videos belonging to the 14 objects and 10 action categories. Below are the statistics of objects frame distribution and affordance mask distribution. We compared our dataset to most relevant existing object affordance datasets. Below table is showing the significance of FPHA affordance over the existing datasets. Objects in existing datasets, either they are non-occluded and there is no interaction involved, or
no pixel level labels are available. To build baselines for our dataset, we use these general settings. We adopted semantic segmentation approach. With dialectical convolutional strategy, we use VGG60 and ResNet15 as our backbones.
We experimented most popular semantic segmentation architectures to build our baselines, including FCN, DeepLab, InigNet, FastFCN. This table shows the performance of different architectures on our proposed dataset. Here's a demo of different semantic segmentation architectures on FPHA-Afford dataset. In conclusion, we highlighted a new problem in robotic vision, proposed a new benchmark dataset. We provided baselines for our proposed dataset. Our dataset and experimentation code will be made publicly available on below given GitHub link. In future, we aim to collect more data and design task-specific model for human-object robot interaction.